In Chapter 14, Section 7, we're going to look at maximum and minimum values of these multivariate problems. So let's jump right in. Problem 1 has kind of a contour map. So a contour map you may have seen before. It shows these lines and they represent either elevation or valleys. And so we see this picture down here in the bottom left, and as the lines get closer or farther away, that indicates a change in elevation, say. Now this is kind of a nice map in that they've shown us the elevation with these numbers like 0, 1, 2, 3, 2, 3, 7 going along this diagonal here. And so just by looking at this, if we were to think of this as height, it's getting higher from 0 to 3. Let me see if I can do this. So the elevation is getting higher to a maximum of 4 at that point. And then actually it gets even higher going this way, so it's even higher over here at 6. And then it decreases here to a minimum probably at that point. So this is like a minimum elevation. This is a maximum over here. And this 4 might be what we call a local maximum, because it's a point that switches from, on either side of it there are smaller numbers. So there's some potential here to test a few of these different points. And that's what we're going to do, is find these points where you have a minimum or maximum, say in this example like an elevation problem. Okay, so how do we do it? We do it by computing what's called the second derivative test. So we introduce this term d for second derivative test, and we're going to say that is d of some point AB, and that equals the second partial derivative of the function with respect to x at the point AB times the second partial derivative with respect to y of the function evaluated at AB minus the partial derivative with respect to x and then y of the point AB squared. So it looks like a lot, but we'll break it down and do it chunk by chunk. Okay, then there's 3 cases. A, if this value d is greater than 0 and the second partial derivative of x at AB is bigger than 0, then we're going to say we have a local minimum. Local minimum at that point AB. B says, the second condition says, if d is greater than 0 again, so same condition so far, and your second partial derivative of x with at point AB is less than 0, then you have a local maximum. And then point C, or the third condition, states if d is less than 0, then you have then no max, oh I better be careful, local max or min. And it might be what we call a saddle point. So a saddle point is just what it sounds like if you imagine a saddle. Boy, am I going to actually try to draw this? I guess so. So a saddle kind of goes up and down on both sides from both directions. Probably am butchering this. Not much of a horseman. Okay, but in a saddle you kind of have this point where it might not be a local max or min, but the derivatives, those tangent lines, are kind of perpendicular. So that's what a saddle point would look like if I haven't butchered this drawing. Okay, so those are the 3 different cases we can have. Now let's see how to put it into action. So our function is, oh, and I should say the points A, B are what we call critical points. So you can have more than one. And they come from where f of x equals 0 and f of y equals 0. So partial derivative, the first partial derivative of f with respect to x and the first partial derivative of f with respect to y, where those are equal, that's where we're going to get these critical points a, b that we'll test into this equation. Okay, so here's our first function. We have function xy is equal to 4 plus x cubed plus y cubed minus 3xy. And by this point in the course, I don't think partial derivatives should be all that challenging to us. So fx would be 3x squared, the 4 goes away, y cubed goes away, and we're going to get minus 3y. And then we're going to have okay, and at this point we're going to try to find what we call this critical point. So we're going to set that equal to 0, and we can move the 3y over, and we'll get 3x squared equals 3y. Divide both sides by 3, and we'll get x squared equal y. Now we're going to sit on that because we're going to have to do something with that in a minute. Okay, now we're going to calculate the first partial derivative with respect to y. So the 4 goes away, the x cubed goes away, you're left with 3y squared minus 3x. Again, we set that equal to 0, and we're going to get 3y squared equals 3x, or we're going to get y squared equals x. And basically we have two equations, 1 and 2, and the way to solve these would be, this isn't a great first example, unfortunately, because we can't just solve this immediately and get numbers. So you got to kind of think. If x and y were both 0, that would solve this. So you get 0 on the left, 0 on the right, 0 on the left, 0 on the right. Both equations would be equal to 0. So that's one possible point. Another point is if they're both equal to 1. So 1 squared is 1 equals 1 on the right. And then for equation 2, 1 squared is 1 equals 1 on the right. So we have 2 points to check, 0, 0, 1, 1. And if you play around with those equations, you won't be able to find any other numbers that work. So those are the 2 points we have to check. So now let's find this D equation. So we need the second partial derivative. So we need fxx. Let me see. Let's start with a different color so we can see what we're doing now. So let's do fxx in green right next to it. That would be 6x. And then we also need fxy, so let's write that right up here too. So if you look at fx, 3x squared minus 3y, now I'm doing it with respect to y, so 3x squared becomes 0, and negative 3y would become negative 3. Okay, then let's find fyy. That would be equal to 6y, and there we have it. So we could plug in our numbers right now and do it, but I prefer to use letters until the very end, and then we can solve. So the second derivative test at any point a, b is going to equal fxx at a, b. So fxx is 6x times fyy, which is 6y, minus fxy squared. fxy is negative 3, but we're squaring it. So the second derivative test at any point we want to test should be 36xy. This is minus 3 squared is 9, but it's a minus in front, so minus 9. And now we can test our 2 points. So let's try 0, 0. So the second derivative test at 0, 0 would give us 36 will go away. It's going to be minus 9. So we have D at 0, 0 is less than 0. So that's condition 3. So we're going to have a saddle point there. And you can see I put that in the first box and called it a saddle point. Okay, now we try 1, 1. So the second derivative, oh, I should have put 0, 0 in here. This is where we did evaluate 0, 0. Oh, no, not at that point. Apologies. That was still AB. Because it was still x, y, so I guess I could write it as x and y. And then we plugged in A, B being 0, 0. Okay, so let's plug in 1, 1 into 36xy minus 9. We'd get 36 times 1 times 1 minus 9, which is 36 minus 9, which is 27. And that is bigger than 0. And now we have to check fxx at AB. So fxx at the point 1, 1 is equal to 6 times 1. So fxx is right here. And that's equal to 6, which is bigger than 0. So that is going to be condition A. D was greater than 0, and fxx AB was greater than 0, so that should be a local min. So the local minimum of this occurs at 1, 1. And I had almost predicted this before we even did the problem. So I said, oh, these numbers are getting smaller, and it looks like it's occurring at 1, 1. So that was the minimum value. And I said, oh, they're increasing this way, and they're increasing this way, going away from each other. So notice this is going to form like another way to think of a saddle point is if you put a ball on it, it would want to roll off of it. So if you put a ball on this 4 here, it's going to want to roll down into this valley or down this other side. So kind of a classic saddle pointer. So this was a min, and this one was a saddle point. And we proved that with our second derivative test. Okay, so that's problem 1. It's kind of a long one because this is the first time I've shown you these ideas. Now the rest should go a little quicker because we're going to repeat this kind of process over and over. Okay, for problem 2, I'm going to try to leave this stuff up on the screen. Now if we end up needing more room, we'll probably clear that out as we do more of these because hopefully it'll catch on. So we have this function and we want to find local mins and local maxes and saddle points. So we're going to do the exact same thing. The function is 4 minus 2x plus 4y minus x squared minus 4y squared. And first we're going to find fx, which should be negative 2 minus 2x, and that's it. And we can set this one equal to 0, and we can solve this one directly. X should equal negative 1. So move the 2 over, it becomes positive, divide by negative 2. We should get x is negative 1. That's one of the critical values. Fy is going to be equal to 4. 4 goes away, 2x goes away, 4y becomes 4. X squared goes away, minus 4y squared becomes minus 8y. And if we set that equal to 0, you should be able to easily see or solve that y has to equal positive 1/2. Okay, so those are the points we're going to test. Now we find fxx, and from this it's just going to be negative 2 goes away, negative 2x will be negative 2. Fyy is going to be negative 8, and the third thing we need is fxy. Go back to the fx equation, there's no y's in it, so it's going to be 0. So I can't even really plug in these numbers because there's no x's or y's left in the equation. So we write it, d is equal to fxx, which is minus 2, times fyy, which is minus 8, minus fxy squared, which is 0 squared. So we're going to get, this is positive 16 minus 0, which is just 16, which is bigger than 0. So we do have a local min or max. Then we have to check fxx, and fxx was negative 2, which is less than 0. So we have d greater than 0, fxx less than 0. This is case B. Therefore, we have a local min. And it says, oh, I looked at the wrong thing. Local max. My apologies. I read the wrong one. So case B, we were right there. It says local maximum. So this is a local max. So we know we have a local max. Well, what's the number? Well, this is where you do have to plug in your A and B. So we're going to plug in -1 for x and 1/2 for y into the original function. So we get 4 minus 2x, which would be 2 times -1, plus 4 times y, which is 1/2, minus x squared, which is -1 squared, minus 4 times y squared, which would be 1/2 squared. And we're going to get, this would be 4 plus 2 plus 2 minus 1 minus 1. So we have 6, 8, 7, 6. So add all those up and you'll get 6. Now because there are no other critical points and the second derivative test is just constants, there's no x's or y's to even plug into, there cannot exist a local max or any saddle points. So we would put D and E does not exist for both. Okay, let's try problem 3. Okay, in problem 3 it says find the local max and min and saddle points of the function, and the function they give us is 3e to the x cosine y. And the first thing we find is fx, which is going to be 3e to the x cosine y. So cosine y would be looked at as a constant, so it's going to stick around for the ride. So does 3. And the derivative of e to the x is e to the x. So fx does not change at all. Now here's the thing about this. The fxx will also not change at all. So we can get those right away. And let's find fxy while we're at it. So this one will change slightly. If I look at 3ex cosine y and I take a derivative with respect to y, we're going to get the derivative cosine, which is negative sine. So it's going to be negative 3ex times the sine of y. But since fx was the same as the original equation, then this also has to equal fy, since we did a derivative with respect to y. And then fyy would be the derivative of this with respect to y. Now the derivative of sine is cosine, so it's negative 3e to the x cosine of y. Okay, so we have fx, fy, fxx, fyy, and fxy, all 5 of the things we could possibly want. And if we set, actually I don't think I'm going to look for critical points, and you'll see why in a second. So what we're going to do next is we're going to solve for d. So d is going to be fxx, which would be 3ex cosine y, times fyy, which would be negative 3ex cosine y, minus fxy squared. fxy was negative 3e to the x sine y. But we're squaring that. So if I combine like terms, we're going to get 3 times minus 3, which is minus 9. Ex times ex is e to the 2x. So those x's add when you multiply this similar base. And then we have cosine y times cosine y, so we're going to get cosine squared y. Then when I square this, I'm going to get minus, this is going to be minus 3 squared, which is positive 9, e to the 2x sine squared y. And what we're going to see, actually I'll write it out, we get minus 9e2x cosine squared y, minus 9e to the 2x sine squared y, and we can factor out a common minus 9e2x from both terms. So we factor out a common 9e to the 2x times the quantity. What's left over is cosine squared y. If I factor out this minus sign in the middle, it becomes plus sine squared y. And those of you who have remembered your trig properly will realize that cosine squared y plus sine squared y is 1. So the second derivative test d is equal to minus 9e to the 2x. Now e to the 2x is always a positive number. There's no x value you can pick that's going to make this negative. So this is like negative 9 times some positive number. Now that will always be negative. So this is going to be some negative number, which means d has to be less than 0. So we are forced to be in case C. Okay, but it turns out that we're not going to even have a, so we definitely don't have a max, we definitely don't have a min, because d cannot be greater than 0. And it turns out that since fx and fy, they can be 0, but they're only zeros at points where y changes, but the second derivative test doesn't even include y. Look at, the only variable is x. We're also not going to have a saddle point. So there are values of y that make fx and fy 0, but those values of y are not going to affect the second derivative test at all, so they have no effect. So nothing exists in this particular picture. So we have DNEs all across the board. Okay, and I thought it'd be useful to show you on GeoGebra 3D what this picture looks like, so you can see it's kind of these cosine curves that are also on an exponential increase in the z direction, and so they definitely don't have max or mins, and there's the saddle points. You can't see those either, so I can't really see a point where there's kind of this saddle effect where I would put a ball down and it would kind of roll into any particular direction. Okay, so and these problems you don't need GeoGebra 3D graphing to do them, but it can help to look and see what they would look like. Okay, problem 4. We have find the absolute max and min values of f on set D. Okay, all right, these are, let's see. Nope, we'll still want, I believe, we will still want our equation up here, so let's give it a try. So we have, actually in this one we first want to draw this, I wish I didn't use D, so we've already used D for the second derivative test. In this one they want it to be like the domain, or set D of x and y values. So they said, okay, x varies from 0 to 4, and y varies from 0 to 5, and so that's going to give us this region that looks like this. This is D. Okay, now a max or a min should occur at one of the corners. So we have to identify those corners. 0, 0, this would be 0, 5, this would be 4, 5, and this would be 4, 0. Okay, so we're going to just kind of write that out and leave those points there for now. Okay, then we're going to see that f of xy is equal to 4x plus 6y minus x squared minus y squared plus 7. And we will immediately find our values. So fx would be 4 minus 2x, and we can set that equal to 0 and get x has to equal 2. I should mention, max or min can occur at the corners or anywhere in here. So anywhere in this box, a max or min could occur. So that box kind of restricts our search space to try to find these max and mins. Okay, but we can use this critical method to find these critical points by setting the first partial derivative equal to 0. Okay, now we do fy, which is going to be 6 minus 2y. Set that equal to 0, and we find that y should equal 3. So we immediately have a point, 2, 3, that we should check. And if we look, that point would be 2, 3. That point would be right about there. So it's definitely in contention. It's a possibility because it's in our box, our D box. Okay, now we're going to find f double x, which is -2, fxy, which is 0, and then fyy, which is -2. So the second derivative test, notice it doesn't even matter at 2, 3, would be fxx, which is -2, times fyy, which is -2, minus fxy, 0 squared. So this is going to be +4, which is bigger than 0. And then we check fxx, which was -2, which is smaller than 0. So we have d bigger than 0, fxx smaller than 0. We again have a local maximum at this point, 2, 3. So we plug it in to the function, and we get f of 2, 3 equals 4 times 2. So I'm plugging into each of these letters here, plus 6 times y, but y is 3, minus 2 squared, minus 3 squared, plus 7. And being Calc 3, I hope I don't have to show you each of these arithmetic steps. If you crunch this out, you will get 20. Okay, which we are thinking is a max. But you also have to test these 4 other points. So it's kind of best to make a table. So we pick x, we pick y, and we pick the function. And I'm not going to go through all these substitution steps because I believe you can handle that. But you have to check x is 0, y is 0. We have to check x is 0, y is 5. We have to check x is 4, y is 0, and x is 4, y is 5. And if you plug those in, I'll just give you the results. When you have double zeros, the function is 7. When you have 0, 5, the function turns out to be 12. When you have 4, 0, the function turns out to be another 7. And when you have 4, 5, you get another 12. So out of all these numbers, 20 was the biggest. And out of all these numbers, there's a tie for smallest at 7. But they didn't ask us where these occur. They just asked us what they were. Biggest number is 20, smallest number is 7. So that is how you would do problem 4. Okay, problem 5. We have absolute max and min on the set. D, very similar. First thing we should do is get a picture for what this D is. So this x squared plus y squared less than or equal to 1 is a circle centered at the origin with a radius of 1. So I put a little line 1, 1, minus 1, minus 1. The D region is a circle like that. So this is D. Now there's no clear point here to try. So what you should do is just try the 4 clear points that we use. So this would be 1, 0. This one would be 0, 1. This one would be minus 1, 0. And this one would be 0, minus 1. So those are the 4 points you'll pick, but anything inside of that circle could also be a potential min or max. So we have to go through our steps again. The function xy is equal to 2x cubed plus y4 plus 9, which gives us fx equaling 6x squared. And notice if I set that equal to 0, I get x equal to 0. Then we find fy, which would just be 4y cubed. And again, if I set that to 0, I get y equals 0. So there could be a contender right here at 0, 0, a critical point. Okay, then we find the other things. fxx would be 12x. fxy would be 0. fyy would be 12y squared. Therefore, D is equal to fxx, which is 12x, times fyy, which is 12y squared, minus fxy squared, which would be 0 squared. This is going to equal, make sure I don't make a mistake, 144 xy squared. And we would want to check all of our points. Okay, now if you plug in the point 0, 0 into this, you're going to get D equal to 0, which doesn't match any of our three cases up here. So what we have to do is just form our table x, y, f, x, y, and we're going to try these points that we've found so far. So we're going to try 0, 0, this first critical point we had. Then we can try 1, 0. Then we can try 0, 1. Then we can try minus 1, 0, just going counterclockwise here. And then the last one's 0, minus 1. And again, I'll save you the substitution step. If you plug this in, 0, 0, everything goes away, you get 9. 1, 0, you should get 11. 0, 1, you should get 10. Minus 1, 0, you should get 7. And 0 minus 1, you should get 10. So out of all of these, there's a tie. No, there's not a tie. The maximum is 11. It occurred at 1, 0. The minimum is 7, and that occurs at minus 1, 0. So we have the maximum here, and we have the minimum across from it on the x-axis at minus 1, 0. And you can see I put those numbers in here, 11 and 7. Okay, so just looking for those numbers. That should do it for problem 5. Okay, for problem 6, we have find the points in the cone z squared equals x squared plus y squared that are closest to the point 4, 2, 0. So we have this three-dimensional cone, and we have a point in 3D space, and we want to see what points are closest to, what points on the cone are closest to this point floating in space. So to get this, we need another D, but this time it's distance formula. So distance formula equals x minus x0 squared plus y minus y0 squared plus z minus z0 squared. And we're going to have this point is x0, y0, z0. So this distance formula will become the square root of x minus 4 squared plus y minus 2 squared plus z minus 0 squared. And let me write this over here, simplified even a little more. Distance formula will be x minus 4 squared plus y minus 2 squared plus z squared. And in all these problems, you want to eliminate z. So z, we only want these. Notice that our second derivative test only includes x and y. So we always want to write these as functions of x, just x and y. And it's kind of nice because it says the cone is defined by z squared equal x squared plus y squared. So we're going to replace this z squared with this, x squared plus y squared. So the distance formula we're trying to minimize, so we're trying to minimize the distance, is x minus 4 squared plus y minus 2 squared plus z squared, but we're replacing z squared with x squared plus y squared. Okay, now there's a trick here. We can either minimize this formula, which when we start taking partial derivatives is going to be very ugly because it has a square root on top, or we can minimize d squared, which is what we're going to prefer to do. So we are going to square both sides, and we're going to get x minus 4 squared. This is a trick you probably wouldn't think of unless I showed you. Minus 2 squared plus x squared plus y squared. Okay, so that is what we're going to try to minimize, is the distance squared. And in essence, if we minimize the distance squared, we're also minimizing the original distance. Okay, so now we're going to find fx and fy as we have done. So let's see if we can, so this is our function now. This is our function of xy. Therefore, fx would be, now be careful, the derivative of x minus 4 squared would be 2 times the quantity x minus 4 to the first power times the derivative of the inside, which would be 1 minus 0. So this is chain rule and power rule combined. And then y minus 2 squared would go away, and then we get plus 2x, and y squared would go away. And this is going to equal 2x minus 8 plus 2x, which will be 4x minus 8. And if we set that equal to 0, because we're looking for the critical point, we should get x equal to 2. Okay, then we find partial derivative of f with respect to y. Very similar. It's going to be 2 times the quantity y minus 2 to the first times the derivative of the inside, which would be 1 minus 0 plus 2y. And that's going to equal 2y minus 4 plus 2y, or we're going to get 4y minus 4 equals 0, therefore y is 1. So that's our critical point. Our critical point is x is 2, sorry, and y is 1. It's 2 comma 1. But we don't know what z is. So to get z, we're going to plug 2, 1 back into this equation. Z squared was x squared plus y squared. So we're going to say z squared is equal to x squared, which is 2 squared, plus y squared, which is 1 squared. Therefore, z squared equals 4 plus 1, 5. Therefore, z is equal to plus or minus the square root of 5. So our final answer is 2 comma 1 comma plus or minus root 5. That point, which is on the cone, should be the closest to the point 420. And there's 2 of them, so there's some symmetry here. And so you would just type 2, 1 minus root 5 for the smaller z value, 2, 1 root 5 for the larger z value. And that'll get you problem 6. Okay, for the last set of problems, we no longer need the second derivative test, so I'm going to clear that away. Give us some more space to work with here. And problem 7 is a word problem, so it says find 3 positive numbers whose sum is 200 and whose product is a maximum. So 3 numbers whose sum, which means we're adding them together, equals 200, and whose product is some maximum. Okay, so like I said before, one of the first things you want to do is get rid of z. So we're going to use the first equation to solve for z. So we would just subtract x and y from both sides and get z. Now we're going to plug that in for this z right here in the maximum equation. So this is going to be x times y times the quantity, 200 minus x minus y, and that is the function that relies only on x and y that we want to maximize. Okay, so we'll distribute. We'll get 200 xy minus x squared y minus xy squared, and that is our fxy. And now we can go through like we would normally. Find fx. The first partial derivative with respect to x of the function would be 200y, so the x will just go away in that term, minus 2xy minus y squared. Okay, so y is seen as a constant, and then same rules apply for x as the variable. If it's x to the first power, it goes away. If it's x squared, the 2 comes down, etc. Now we're going to set that equal to 0. And if you look very closely, you can isolate x. So I can see x is all by himself right there. If I can unbury him, I will have something I can work with. So we're going to rewrite this as minus 2xy equals, pull the 200y over by subtraction, add y squared to both sides. Now to isolate x, you'll just divide everything by minus 2y. So we'll get minus 200y plus y squared all over minus 2y. And that can be simplified into, this is going to be 100 minus 1/2 y. So you have a y in every term, so you can cross off at least one y from every term, and then divide everything by 2. So 200 becomes 100, minuses cancel, and the 1 in front of the y will become 1 over 2 with a minus sign, and there we have it. Now we're going to find fy. Fy would be equal to 200x minus x squared minus 2xy. But we're going to replace all instances of x with this that I just circled, that we just found. And we're going to set this equal to 0. So fy is really going to be 200 times 100 minus 1/2 y minus 100 minus 1/2 y quantity squared minus 2 times 100 minus 1/2 y times y. So if you look at that, I replaced all instances of x in the fy equation with the 100 minus 1/2 y. And now if you look, there are no x's in this equation. It's all y's and numbers, and it's equal to 0. Now you've got a lot of distributing to do and some foiling and some combining like terms. If you do that, you should end up with the following: 3/4 y squared minus 200y plus 10,000, and that has to equal 0. And then to make your life a little easier, you can multiply everything by 4 and get 3y squared, so there's no fractions, minus 800y plus 40,000 has to equal 0. And that will factor into the following: y minus 200 times 3y minus 200 equals 0. Now this gives us two answers for y. One is when y is equal to 200, and the other is when y is equal to 200 divided by 3. Now y equal to 200 would make no sense. If y was equal to 200, the other two numbers would be equal to 0. And then when you try to maximize their product, it's just going to be 0 because two of them are 0. So we're not even going to work with this one. It doesn't make sense to. But let's try y equal 200 over 3. So the first thing we're going to do is we're going to back substitute that into our x equation. So we know x is equal to 100 minus 1/2 of y, but y is 200 over 3. So we get x is equal to 100 minus 100 over 3. And that is also equal to, when you combine lowest common denominators, 200 over 3. And then finally, we just have to find z. Z is equal to 200 minus x, but that's 200 over 3, minus y, which is 200 over 3. And if you do that arithmetic, you get z is also 200 over 3. And so all three numbers are 200 over 3. And this is kind of a common theme. Basically, if you're adding numbers, like two numbers would represent a square, and a square is the most efficient volume. So we'll give you the biggest volume for the size for the sides. And then in 3 dimensions, this would be a cube. So you'd have a cube, 200 over 3 on each side, and it would be the most efficient, in this case, a volume, when you multiplied all 3 sides together. So just take the number they give you, divide by 3, and that would be your 3 answers. But this is how you technically solve it with what we've learned. Problem 7. Okay, for problem 8, they want us to take a sphere and we want to inscribe a box inside of it. So I'm not going to try to draw this in 3 dimensions because I'll butcher it. But if we have x and y, and just think about that, we have a sphere. And we're trying to inscribe a box inside of it. Well, in 3 dimensions, this box would have this distance from here to this green point would be x, and that would mean this is minus x. This distance from here to here would be y, and then this would be minus y. But if we think about the absolute distance, it's really just 2x and 2y. So the volume of this box, the volume of the box, would be the x direction, which is 2x's, the y direction, which is 2y's, and then in the same third dimension, in z, this is going to be 2z's. And this is going to be 2 times 2 times 2, which is 8xyz. And this is what we are trying to maximize. So we want to maximize this formula. Now the other formula we need is the equation of the sphere. So the equation of the sphere in 3 dimensions is x squared plus y squared plus z squared equals some radius squared. And we're only going to use that to eliminate z. So from this, we're going to solve for z and say z is equal to r squared minus x squared minus y squared square rooted. Okay, and then we're going to take all of that and we're going to replace the z in this equation with that formula. So we're going to get volume of the box, which is really the function we are trying to maximize, so let's write it as fxy, is equal to 8xy times the square root of r squared minus x squared minus y squared. Okay, now we're going to do our partial derivatives. So our partial derivative with respect to x would be, now you have to use product rule because you're multiplying 2 different functions. So product rule says take the derivative of the first with respect to x would be 8y, leave the second alone, so it would be square root r squared minus x squared minus y squared, plus leave the first alone, 8xy, times the derivative of the second, which would be 1/2 times the quantity r squared minus x squared minus y squared raised to the negative 1/2 times the derivative inside with respect to x would be minus 2x. I know it's hard to see that. I'll write it cleaner right here. So f of x is going to equal 8y times the square root of r squared minus x squared minus y squared plus, let's see if we can do some simplifying. This minus 2 and x are going to multiply into this 1/2, and the 2's will cancel, and this x will combine with that x. So we're going to get, in the numerator, 8x squared y, and in the denominator, we're going to get the square root of that same value, r squared minus x squared minus y squared. Okay, I know it's kind of hard to see, so let's look at it again. The 1/2 and this 2 will cancel, but I do pick up a -1. In fact, I forgot that -1. There should be a minus right there. I think I looked. And this x will combine with that x to make it x squared. That y will still stick around. Those all go to the numerator. And then the r squared minus x squared minus y squared is raised to the -1/2. -1/2 means it goes into the denominator and it has a square root sign on it. Okay, now we're going to find a common denominator. So we are going to multiply. We're going to take this denominator and we're going to multiply it into this term, but also divide by it. So notice this term, these two terms are the same, so when I multiply them together, the square root is going to go away. So let me see if I can do this. We're going to have, need space for this, fx is equal to 8y times r squared minus x squared minus y squared minus 8x squared y, all on top of this denominator, r squared minus x squared minus y squared. Okay, now we are setting this equal to 0. The only way that this function can be 0 is if the numerator is 0. In fact, we don't want the denominator to be 0, because if it is, we have divide by 0 error. So in essence, now that I have a common denominator, we can totally forget about the denominator. And we're just going to look at the numerator and set that equal to 0. So let's expand this numerator out and combine some like terms here. We have 8r squared y minus 8x squared y minus 8y cubed minus 8x squared y. And if you look, we will get 8, let's see here. I thought we would get something to cancel, but it doesn't look like it. We're going to get 8r squared y minus 16x squared y minus 8y cubed. And that has to equal 0. Okay, so now we're going to look at fy. So fy, if you do this, because of symmetry, the only thing that's going to change is the derivative is going to be 8y now, 8x, sorry, and then everything else, not quite, let's see, we're going to 8x square root r squared minus x squared minus y squared. Then it's going to be plus 8xy again, but then it's also going to be 1/2 times that same stuff to the minus 1/2, but then we're going to pick up a negative 2y. Okay, so fy will be, we're going to get 8xy times the r squared minus x squared minus y squared plus the 8xy, and then over the same denominator that we didn't care about, that we threw away. Oh, but I forgot this would be squared. Okay, so let me look at this carefully. This is not an easy problem. Okay, and I did make a couple errors there. So there is no y term here, and this should have been a minus. Okay, and I believe I don't want to expand like I did here. I don't think we want to do this, if I recall. So let's go back to what we had. Just that numerator. So we have from fx, setting equal to 0, we have 8y times r squared minus x squared minus y squared minus 8x squared y equals 0, but I'm going to just set that equal to 8x squared y. So for this to be 0, basically what we're saying is, for this numerator to be 0, this term has to equal this term. It's the only way those can be 0. Okay, now we can say, oh, 8y on the left, 8y on the right, those will cancel. And therefore, x has to equal the square root of r squared minus x squared minus y squared. Now technically it's plus or minus, but it makes no sense to have a negative distance, so we're going to get rid of that minus sign. So we're saying no, doesn't come into play. Now if you look at the fy equation, you get something very similar. You're going to get 8x r squared minus x squared minus y squared has to equal 8xy squared. And just like before, we're going to come in here and say, oh, 8x cancels with 8x, and so we should get y squared equals that, so the square root of that, r squared minus x squared minus y squared, has to equal y. And we will plug those into, so those are our critical values, and we'll plug those into the maximum equation. Okay, actually, before we plug in, we're going to plug in one of these into the other. So what we're going to do is we're going to say, let's work from the blue equation. So we want to solve for x squared. So we're going to square both sides. So we're going to get r squared minus x squared minus y squared equals x squared. But we're going to add x squared to both sides, and we're going to get r squared minus y squared equals 2x squared. And then x squared is going to be 1/2 r squared minus 1/2 y squared. And that is going to go into our y equation. So we're going to get, in green, we have, let's see here, let's square both sides. We're going to get r squared minus x squared minus y squared equals y squared. But x squared is really 1/2 r squared minus 1/2 y squared, but there's a double negative there. So plus 1/2 y squared equals, when you add this other y squared, you're going to get 2y squared. So there's a couple steps in one there. And we're going to subtract 1/2, so we're going to get r squared minus 1/2 r squared is 1/2 r squared equals 2y squared minus 1/2 y squared will be 3/2 r squared. Oh, y squared. Then we are going to divide by 3/2 or multiply by 2/3. So we're going to get 1/3 r squared equals y squared. Or y would be r over square root 3. So take a square root of both sides. Okay, a lot of work. I realize this problem is kind of a beast. Okay, so that's why. Now we're going to back substitute that into x to solve for x. So where was x? So let's look right here. Let's do blue. We're going to have this y squared right here will become r squared over 3. So we're going to get 1/2 r squared minus 1/2 y squared. But y squared is going to be r squared over 3 equals x squared. This is going to give us 1/2 r squared minus 1/6 r squared. Let's see, this is 1/2 r squared minus 1/6 r squared equals x squared. 1/2 minus 1/6 would be 3 over 6 minus 1 over 6 would be 2 over 6, which is 1/3. So this is going to be r squared over 3 equals x squared. And if you take a square root of both sides, you're going to get, surprise, surprise, x is r over root 3. So we have x, we have r, we have x and y, and we can now solve for z. So z, boy oh boy, I'm out of room here. Z is the square root of r squared minus x squared minus y squared. So z is going to be r squared minus x squared, which would be r squared over 3, minus y squared, which would be r squared over 3, square rooted. This is like 3 r squareds over 3, so you have 3 minus 1, which is just 1 r squared over 3, square rooted. And so we get z is also r over square root 3. So once again, the most efficient rectangular shape we can cram into a sphere is a cube. So all three sides are the same, and they have the length of r over square root of 3. So the last step is to plug that into the volume of the box equation. Now I'm just going to start fresh because it looks awful right now. So we have x is r over root 3, y is r over root 3, z is r over root 3. And the volume of the box we found right away to be 8 times x times y times z. So the volume of the box is going to equal 8 times r over root 3 times r over root 3 times r over root 3, which is 8r cubed over 3 root 3. So 2 of those root 3's can become 1/3 with a root 3 left over. And that is the answer. Okay, so a challenging problem, I realize, but there it is. Okay, problem 9 isn't quite as bad. We have a cardboard box that we want to make, and it says let x, y, and z be the dimensions of the cardboard box. So basically we have cardboard box, and we will okay, so it looks something like this. This is the x direction, y direction, z direction. And it says the volume of this, the volume, which would be just x times y times z, has to be equal to 4,000 cubic centimeters. But they want to minimize the amount of cardboard used. So cardboard would be the surface area of this box. Now it says it has an open top, so we have a a bottom and then 4 sides and no top. So if you look at this, the surface area would be the bottom, which is x times y, plus the 2 sides in the front and back, which would be x times z. You have 2 of those. And then we have 2 sides that are y times z. But we don't want z. So we're going to solve for z right away from the volume equation, and we're going to call z the 4,000 volume that we want divided by xy. So surface area that we're trying to minimize would be x times y plus 2xz's, but we're going to replace z with this term here, 4,000 over xy, plus 2yz's, but we're going to replace z with this term here. And then we can distribute this 2 and cancel those x's, and we'll get 8,000 over y. And then similarly, we will distribute this 2 to the top and cancel these y's and get 8,000 over x. And I'll probably write this just to make the derivatives easier. X, y plus 8,000 y to the minus 1 plus 8,000 x to the minus 1. 8,000, not 80,000. Okay, now we just, and I should say this is our function. So this is xy. So the first thing, find fx. It's going to be y. The 8,000 y minus 1 will go away, become 0, it's just a constant. The minus 1 will come down, get minus 8,000, x to the minus 2, and we're setting that equal to 0. So we have y equals 8,000 over x squared. Okay, so that's one answer. Now we look for fy. Fy would be x. The minus 1 will come down, negative 8,000 y to the minus 2, and then the 8,000 x minus 1 will also go away. Set that equal to 0, and by symmetry we'll get x is equal to 8,000 over y squared. Okay, so it doesn't matter which way we go. I'll take this 8,000 over y squared and plug it into this x squared here. So we're going to get y is equal to 8,000 divided by 8,000 divided by y squared squared. And this is going to equal 8,000 over, I'm going to write it as 8,000 squared. Let's not actually do that out. Over y to the 4th. Okay. Now we are going to, now we're going to subtract that over, actually, let's write it like this. This is going to be 8,000 over 1 times, flip that fraction, so it's going to be y to the 4th over 8,000 squared, and that has to equal 0. Now the 8,000 on top will cancel one of these 8,000s here, and we're going to get y minus y to the 4th over 8,000 has to equal 0. And we're going to factor out a common y and get 1 minus y cubed over 8,000 has to equal 0. Now there's two solutions to this. One is when y is 0. But I argued before that we shouldn't let that be a solution for a previous problem, because that means this box would have no y dimension and therefore would be a flat piece of paper. So the only thing that makes sense is if we set this bubble equal to 0. So 1 minus y cubed over 8,000 has to be equal to 0, which means 1 has to equal y cubed over 8,000. Multiply both sides by 8,000. Y cubed has to equal 8,000. And y has to be the cube root of 8,000. Only plus would matter because this is a physical problem, so we have positive dimensions. And lucky for us, this is a nice even 20. Okay, so y is 20. If you plug that 20 in for y, back, let me use a different color. If we plug 20 back into this equation for x, we will get x is 8,000 divided by 20 squared, which is 8,000 over 400, which is also 20. Surprise, surprise. Once again, these dimensions are that of a square. So this is a square box. Now it would be a cube if z is the same value, but let's check it. Z is this equation here. Z is equal to 4,000 divided by x times y, but x and y are both 20. So we get 4,000 divided by 400. Z is 10. So this is not a cubic box. This is a cubic. It's a square box that is half as tall as it is wide on either direction. So it's not quite a perfect cube. So the dimensions are x is 20, y is 20, z is 10. And that's how you do that one. Okay, so that's the end of the challenging problems. The last problem states if f has a local minimum at AB and f is differentiable at AB, then the gradient of f at AB equals 0. So let's remind ourselves what the gradient of AB is. That would be the first partial derivative of f with respect to x at AB and the first partial derivative of f with respect to y at AB, and they're saying these are equal to 0. Well, that's exactly what we said were critical points, and you only have max or mins at critical points. So to have a minimum at AB, you must have the gradient equal to 0. So that is true. Okay, and that will complete chapter 14, section 7.